For each molecule or ion, determine the shape and indicate whether each molecule would be polar or nonpolar. Now our first molecule is sulfur dioxide. Look at your periodic table. You can see that both oxygen and sulfur, they're in the same group, group 6, right? So the implication there is they both have 6 valence electrons. Now the very first step that we need to follow here is we got to create just a basic Lewis structure. And so in order to do that, let's take 3 elements. Each of the elements has 6 valence electrons. So we need to account for a total of 18. All right, let's draw our basic structure now. So we know sulfur is going to be in the middle, and it's going to be bonded to 2 oxygens. Now, 2 things I want you to remember as we move forward. Notice oxygen is in period 2, and oxygen becomes chemically satisfied, if you will, when it obeys the octet rule, when it has 8 electrons in its outermost shell. Sulfur, on the other hand, it can't have an octet, that's fine, but the fact that it's in period 3, these elements are different. They can have more than 8 electrons in their outermost shell. So let's not forget that as we progress. Anyways, okay, let's account for all 18 electrons. So far, we got 4 taken care of. So let's go 6, 8, 10, 12, 14, 16, and I'm going to put the last 2 here on the sulfur. Now both of the oxygens, their octets are satisfied, right? But sulfur, it's at least got to have an octet. So what can we do? Well, it can actually share electrons with one of the oxygens and create a double bond. And that's exactly right. Now this oxygen has 8 valence electrons, the sulfur does as well. 2, 4, 6, 8, and then so does this oxygen. Now with a structure like this, there should be a very specific vocabulary word that needs to come to mind instantly, and hopefully it did, and you're thinking, this has resonance, and you're absolutely right. Another possible structure would just be the opposite of that. I'm not going to bother drawing it right now, but I do want to ask you, are there any other structures? And absolutely there is. Besides the one that I just talked about, we could have a situation like this, where now sulfur shares a double bond with both oxygens, and still, remember, we got to account for 18 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. Okay. Well, after you figured out all your basic Lewis structures and you've accounted for resonance and so forth, the next kind of thing to start figuring out would be formal charges. What's the point? Well, the best Lewis and resonance contributing structures, they're going to have the least number of atoms with formal charge. So let's progress forward. Let's call this oxygen number 1 and this one number 2. And we'll figure out the formal charges of the elements here. So the formal charge of oxygen number 1 is the group number, which is 6, minus the number of unbonded electrons. Notice we have 4. Minus the number of bonded electrons divided by 2. So we have 4 electrons divided by 2 is 2. So here, as you can see, the formal charge on this particular oxygen would be 0. So I'll put that off and circle it. Okay. Now, let's do oxygen number 2. Formal charge of oxygen number 2, group 6, minus this time 6 unbonded electrons, minus 2 divided by 2 is 1. So what's the overall charge? -1. Let's make note of that. -1. All right, what about sulfur? Formal charge of the sulfur is group 6 minus 2 unbonded electrons minus 2, 4, 6 divided by 2 is 3. And so that gives us what? +1 charge. Okay, so now we got to say, okay, is this the best Lewis structure for this molecule? We don't know yet. Let's compare it to this one. So notice both the oxygens, they're chemically the same, considering that they both are sharing a double bond with the sulfur and they both have 2 lone pair. So I'm just going to say for this, I'll say formal charge of the oxygens is group 6 minus 4 for the unbonded electrons minus 2, 4 divided by 2 is 2, and therefore their formal charges end up being 0. All right, what about the sulfur? Formal charge of sulfur. This time, group 6 minus 2 unbonded electrons minus 2, 4, 6, 8 divided by 2 is 4. Look at this, folks. Its formal charge is 0. So what does this mean? I'll read the principle again, and please take this down in your notes. The best Lewis or / resonance structure has the least number of atoms with formal charge. So clearly, since all of these have no charge, or charge of 0, if you will, this will be the structure that we're going to use to move forward and actually figure out its molecular shape. The next thing that we have to do is look at your table in your packet. And we have this word steric. And steric essentially, in the most basic meaning, is just an area of electron density. So we're going to look at the central element, and we're going to see its steric number. We're going to count it up. How many areas of electron density? Now, here's the kind of the catch. You have to know that double bonds and triple bonds and even single bonds, they all just count as one steric area or one steric number. So look what we have here. We have, here I'll use a different color. So here's the first steric number for sulfur, here's the second, and then we can't forget about the lone pairs. So we would say its steric number is 3. Okay, so now look at your table and go down to the number 3 under the steric number heading. Now, the next question is, do we have any lone pairs? And if we do, we got to move to the right on this table. And if you look at sulfur, what did we end up having? We had 1 lone pair. So we come over, and now we have the answer. What is the shape of our molecule? It's actually a bent molecule, or angular molecule, if you will. So let's draw a better representation of the molecule. So it would have this bending. This bent type of shape about it. Now look back at the table. As far as angles, we would have to know that this is, or the angle from like here to here is going to be about less than 120 degrees. And so obviously I'm doing it on the board. I don't have a protractor, I can't be precise, but it's a good idea to kind of commit these angle values to memory, at least the most common molecules that we'll contend with. So here's our basic shape. Now, the question, or the million-dollar question, if you will, is this a polar molecule or not? It's definitely bent. Well, now we have to think about electronegativity. And if you remember, because of its position on the periodic table, oxygen is going to be more electronegative than the sulfurs. So we're going to have a pull this way. I'm going to represent it with this arrow. This oxygen, the electrons are going to be pulled a little bit closer to this one. And then at the same time, this one is going to be competing on equal footing. So a lot of the electron density will be towards the oxygens versus towards the sulfur. So the implication there is that this whole area with all the oxygens has a somewhat negative charge. Not completely negative, but somewhat negative because of the denser or the more electron density. Versus the sulfur, this area is going to be somewhat positive. So the answer is yes, sulfur dioxide is a polar molecule. Our next molecule is carbon tetrachloride. So carbon tetrachloride. So let's go through our steps. We need to figure out the total number of valence electrons. Well, if you're looking at your periodic table, carbon is in group 4 and chlorine is in group 7, but we have 4 of them. So 7 times 4 is 28, plus 4 is 32. 32 electrons that we're going to need to account for. Now carbon obviously is going to be in the middle, and it's going to be surrounded by chlorines. So here's our carbon. I'm going to go ahead and connect them all to the chlorines. Or connect them all to the carbon, rather. Okay, so we've accounted for 2, 4, 6, 8. So now we got to go through the lone pairs. All right, the octets are satisfied, so let's go through and count again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons. Now, obviously, this particular molecule doesn't have resonance, so we don't really need to go through the process of calculating formal charges to determine, okay, which resonance structure is the better structure. So we can just go right away. Now, let's think about steric numbers. Again, steric just basically means area of electron density. Carbon doesn't have any lone pairs and its octet is satisfied. So here it has one steric area, if you will. Here would be the second steric number, the third, and the fourth. Now look at your table. Go down to steric number 4. And then because carbon doesn't have any lone pairs, we're going to go to the first structure. And this represents what we're working with here, a tetrahedral structure. And so, if I was going to draw its molecular shape, you can see here, it would be kind of this molecule where we have representation like this one is in the plane, or not in the plane, but like parallel with it. And then this one kind of comes out at us, if you will, and I'm not really going to fill that in all that great. And then we'd say that this one actually goes into the plane, right? That would be the basic idea or the basic molecular geometry. And look at the angle. Go back to your table, and you're looking about 109 degrees between each of the bonds. All right, back to the question at hand. Is this molecule polar? We have to think about chlorine. What's more electronegative, the chlorine or the carbon? The chlorines, right? So that means that there's going to be a pull of the electrons by this chlorine. There'll be a pull by this one. And then this chlorine will also have a strong hold on them. And so will this one. Now the question is, how can these chlorines outcompete one another? And the answer is they can't, right? The pull by this one is basically canceled by the pull on that one. And then the pull on the electrons by this chlorine is canceled out by the pull on the electrons by this chlorine. So we would say that this molecule, because no one chlorine is actually more electronegative than the other, we would say this molecule as a whole is non-polar. CHCl3 is our next molecule. CHCl3. All right, let's go through our process and figure out our total number of valence electrons that we need to account for. Carbon is a group 4, right? Then we have hydrogen. Hydrogen just has one valence electron. And then we have 3 chlorines, and each chlorine contributes 7 electrons. So 21 plus 1 is 22, plus 4 is 26. 26 electrons. Now carbon is going to be right in the middle. And this time it's going to be surrounded by 3 chlorines and the 1 hydrogen. So let's go ahead and draw our bonds to all the chlorines. And then to the 1 hydrogen. Now let's fill the octets, or satisfy the octets of the chlorines. Because carbon's already done at this point. Alright, we need 26 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and 26. Okay, great. Does this particular molecule have resonance? No, it does not. That's exactly the molecule here in front of us. So we need to ask ourselves, okay, what is the shape of this thing? So let's figure out the steric areas or the steric numbers around the carbon. Here would be a steric number, so would this one, so would this one, and so would this one. So you're looking at a number 4 as far as like your steric number. So go to your table, and you can see that we're dealing with steric number 4 and no lone pairs on this carbon. So we're dealing with another tetrahedral molecule where the bond angle between the different bonds should be about 109 degrees. Now, the ultimate question, is this a polar molecule or is this molecule nonpolar? Let's think about this. The chlorines are definitely more electronegative than the carbon, right? So that means that like this chlorine, it's going to be pulling the electrons that way. This chlorine is going to be pulling them down, and this chlorine will be pulling them up. What about the hydrogen? Well, carbon and hydrogen, their electronegativities are basically negligible compared to one another, so there isn't a real strong pull either way. But it's the chlorines is what we have to account for. Now, is the molecule polar? Well, let's go through our process here and think about it like a tug of war between two teams, if you will. If this team, i.e. the chlorine, has the same strength, is equal in strength to this team, which just happens to be the chlorine, therefore they're equal, how can they outcompete or how can they overpower the other? And the answer is they cannot. So the pull by this one basically is negated by the pull of that one. So we're not going to have like a polar molecule going this way or this way. But what about on this side? This chlorine really has no competition versus the hydrogen. So yes, there would be an overall pull of electrons in this direction, thus creating a region somewhat negative and then creating a region of somewhat positivity. So the answer for this one is yes, this is indeed a polar molecule. All right, tellurium dichloride. All right, find tellurium on the periodic table and tell me what its valence electron number is. And you can see it's in the same group as oxygen, so it's got to have 6 valence electrons. And we're going to add that to 2 times 7 valence electrons for the chlorine. So 14 and 6 ends up being 20 electrons, okay? Now, the tellurium is going to be our central element, and it's going to be bonded to the 2 chlorines. Okay, let's account for 20 electrons. So far 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. All right? Yeah, good. Is there any resonance is the next question. The answer is no. This is the molecule. So what do we want to do now? We want to determine our steric number on the tellurium. So technically this would be 1. So would this one be. And then because it has lone pairs, these represent a steric number. So its steric number, this tellurium, its steric number is 4. Now go to your table and go down to 4. Now how many lone pairs did we end up having? We ended up having 2 lone pairs. So look, go all the way to the right and you can see that this molecule is referred to as a bent molecule. Now notice the bond angles. It's much less than 109 degrees. Typically it's about 104.5. So the shape of this molecule would be something like this. We'd have the tellurium, and then we'd have the 2 lone pair, and then we'd have this bent aspect of it. Now go ahead and start thinking ahead and say, okay, well, is the chlorine more electronegative than the tellurium? And you're absolutely right, that is the case. So what does that mean? It means that this chlorine is going to have a stronger hold, a stronger pull on their shared electrons. And the same goes for this chlorine because there's really no difference. So, as far as regions of positivity and negativity, this whole portion of the molecule would be somewhat negative. And then this whole portion of the molecule would indeed be somewhat positive. So as you can see, this is clearly a polar molecule. Now we actually have an ion, carbonate. And carbonate has a -2 charge. So we can't forget that when we calculate our total number of valence electrons that we need to account for. So carbon's in group 4, and we have 3 oxygens, right? Each of the oxygens brings 6 valence electrons to the table here. And then we need to add the 2 additional electrons, since it has an overall charge. The fact that it is indeed an ion. So 3 times 6 is 18, plus 2 is 20, plus 4 equals 24 electrons that we're going to account for. All right, now, carbon's in the middle, and we have 3 oxygens to work with. And I'm going to go ahead and bond them to the carbon. All right, let's start filling in the electrons and satisfy the octet. So here we go. I'll do that on all the oxygens. Do them first. Now, 24 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. But there's a problem. And the problem is dead center. It's carbon. Carbon wants to have an octet. It's got to have the octet rule satisfied. So what can we do? Well, it's very much a simple fix. This oxygen, let's say, shares a double bond. Now its octet is satisfied. We've accounted for all 24 valence electrons. Now ask yourself, does this have resonance? Absolutely it does, but when it comes to calculating formal charges, we really don't need to draw out all the different structures and so forth, because it's just the double bond moving around the molecule. That's it. So this would be the shape. Now, let's go to our table and apply the number of steric, or the steric number, to our molecule here. Remember what I said, double and triple bonds, they count as one steric number. So this is 1, and then here is 2, and here is 3. So go to 3. Were there any lone pairs on our carbon? And no, there were not. So the molecule, or the shape that's to the right, this is the exact shape. It's trigonal planar. Notice the angle between the bonds should be about 120 degrees. So, about 120 degrees. All right. Now for the question, is this considered to be a polar molecule? Well, if you think about it, all the oxygens, they all have the same electronegativity value. So how can they outcompete one another, especially when you have these angles of 120 degrees? It's not 180 where it's like a direct competition. There's an angle there. So it's like they're both, like this one is negating the pull of both of these. And you can just mentally move that around the molecule, and that would be the case. So we would say, no, this molecule is a nonpolar molecule, but before all is said and done, remember the one last step that we have to take when we're drawing Lewis structures of ions. And that is, we have to set it off in brackets, and we have to indicate the ionic charge to the right, the upper right-hand corner, outside of the bracket. So there it is. That's complete. Again, this carbonate ion is nonpolar. Okay, ammonia, Nh3. Nh3 is our molecular formula, and nitrogen is in group 5. So it's 5 valence electrons plus 3 times 1 for the hydrogens, and you're looking at a total of 8. Okay, so let's draw our nitrogen as the central element. We'll just connect it to the 3 hydrogens. Remember, hydrogens only are satisfied when they have a duet, just 2 electrons in their outermost shell. All these hydrogens are satisfied at this point, but what about the nitrogen? It wants an octet, and technically we need it because we've only accounted for 2, 4, 6 electrons, now 8. It has to have this lone pair. Now, count out or determine the steric number rather. And so, here's a steric area, Here's another area of electron density, and here's another one, and here's another. So we have 4. Go to your table and go down to the number 4, but this time we do have one lone pair on the nitrogen. So we're going to move over 2. And you can see that the molecular shape is trigonal pyramidal, or trigonal pyramid, if you will. So it kind of looks like this. I'll draw the nitrogen, and here's the lone pair. And we have the hydrogens. I'm not going to draw like the 3-dimensional molecular shape, just the basic element in straight line bonds. So there's our molecule. Now the question is, what's more electronegative, nitrogen or the hydrogen? And the reality is the nitrogen is, because in addition to electronegativity, it has these electrons, so there is an overall pull of the shared electrons with the hydrogen. So like it would pull, the electrons would go this way, and then of course the same thing's going to be the case for all 3 bonds with all 3 hydrogens. So there it is. So what happens as far as electron density? This area becomes more electronegative, and then this whole side of the molecule becomes more electropositive. So yeah, ammonia is definitely a polar molecule. Sulfate ion. SO4 with a -2 charge. All right, let's calculate our total valence electrons. Sulfur has 6, and then we have 4 oxygens. Each of them have 6. And then we can't forget the 2 additional electrons, since it has an overall -2 charge. So we're going to say plus 2 electrons. So 6 times 4 is 24, plus the 2 is 26, plus the 6 would be 32. 32 electrons that we're going to account for. Okay, so sulfur is in the middle, and I'm going to go ahead and bond it to the 4 oxygens. And then let's satisfy the octet on all the oxygens. Okay, and even sulfur's octet is satisfied. Well, all right. Here's the thing we have to remember. Well, actually, number 1, let's check our 32 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. All the electrons are accounted for. But what we have to remember is that sulfur is in period 3. What did we say about period 3 elements? That they can actually have more than the typical octet. And that would be okay. So what do we need to do at this point? Are there potential resonance structures? And there really are. So what we want to do is let's calculate the formal charge of the oxygen and the sulfur here to determine, is this the best molecular shape? So I'll say the formal charge of the oxygen, they're all the same, would be the group number, group 6, minus the number of unbonded electrons, 6, minus the number of bonded electrons divided by 2, so 2 divided by 2 is 1. Each one of the oxygens has a -1 charge. So let's make note of that. -1, -1, -1, and -1. Okay. Now for the sulfur. It's in group 6, minus 0 unbonded electrons, minus 2, 4, 6, 8. 8 divided by 2 is 4, and that ends up being a +2 charge. That's kind of a problem, guys. Again, if you think about it, go back to that rule, or that kind of guideline rather, about the structures. We want the Lewis structure, or the molecular structure, that has the least number of formal charges of all its atomic constituents. So let's see, what's a possible resonance structure of this molecule? Well, one thing that could happen is we could actually have double bonds. Remember, sulfur, since it's in period 3, we can go beyond the octet. So let's set it up that way. Let's say that we have the double bonds to our central element, being the sulfur, and then out here we have just single bonds to oxygens. Let's call these oxygen 1. and we'll calculate the formal charge. So the formal charge of oxygen 1 would be group 6 minus, they both have 6 valence electrons, minus the 2 bonded electrons divided by 2 is 1. And so therefore, look, 6 minus 6 is 0, minus 1 is negative 1. Negative 1. They do have a charge, so negative and then negative, okay? We're going to call the double bonded oxygens, we're going to call them oxygen number 2 in our formal charge calculations. So formal charge of oxygen number 2 is, they're both 6, minus 4 unbonded electrons, minus 2, 4 divided by 2 is 2. Notice their formal charges are 0 this time because they have the double bond. So 0 and 0. Alright? Last but not least, let's do the sulfur. Formal charge of the sulfur is 6 minus no unbonded electrons, minus 2, 4, 6, 8, 10, 12 bonded electrons, right? Divided by 2 is 6. So therefore, its formal charge is 0. So already, between the two structures, this is the better shape. And this is what we'll use to determine the actual molecular geometry and determine if it's polar at all. Well, how many steric numbers can we get out of this particular molecule here? Here's a steric number, here's an area, here's an area, and here's an area. So go to 4 on your table. And as you go down, again, sulfur doesn't have any lone pairs, so it's just a tetrahedral molecule, is what it is. And each angle between the bonds is approximately 109 degrees. Okay? Now, since this is an ion, we don't really have to worry about polarity, and as you can see, because they're all oxygens, they can't outcompete one another. But there is one other thing that we need to do. Since it is an ion, remember, we need to set it off in brackets and indicate the overall charge. And here they are. Here's the first negative 1 charge, here's the second, so we'll make note of it here and say negative 2. What about carbon dioxide? Carbon dioxide, okay? So 4 valence electrons plus 2 times 6. So we got 12 and 4 is 16 electrons that we'll account for. And we're going to set it off. We'll bond it, single bond it to each oxygen first. And complete the octets on the oxygen. But we can't neglect carbon. Carbon wants its octet full. And so we need 16 electrons. How many do we have so far? 2, 4, 6, 8, 10, 12, 14, 16. That obviously doesn't work. So what can happen here so we can complete the octet on the carbon is double bonds. It can share double bonds with both oxygens, and this is exactly the structure. We don't have to really worry about resonance. I mean, there could be a potential resonance structure where there's a single bond to an oxygen and it has 6 lone pair and all that, but we're not going to worry about that. We want carbon taken care of. Actually, if we did that, carbon would be left unsatisfied. So yeah, this is it, carbon dioxide. Now, let's think about our steric number here. It's got 2 regions. So go down on your table, there aren't any lone pairs. What has a steric number of 2? Well, that'd be a linear molecule. What's the bond angle? The bond angle would be 180 degrees. 180 degrees, okay? That's our shape. Now, as far as electronegativity, because oxygens are on both sides of the molecule, how can one oxygen outcompete the other? And the answer is it cannot. Because, yeah, it's going to pull, and yeah, there's going to be a pull of electrons this way, but basically they negate or cancel each other out. So we would say that carbon dioxide is a non-polar molecule. Boron trifluoride. Boron trifluoride. Now look at your periodic table. Where is boron? You can see it's a group 3 element. So therefore it's going to have 3 valence electrons plus 3 times the 7 electrons that each fluorine contributes to the molecule. So we got 21 plus 3 is 24. 24 electrons that we'll account for. So I'm going to draw the boron. I'm going to go ahead and bond it to the fluorines. And let's go ahead and fill in the octets on the fluorines. And then we'll count up our total number of electrons to see where exactly we are in accounting for all 24. So let's do it. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All 24 electrons are accounted for. But you might be saying, oh, well, wait just a minute. Now, boron, what about its octet? Boron is one of the exception elements. It's okay with just 6 valence electrons. So I would make a little note about that because you'll definitely see this molecule in your future. So boron, it's okay with just 6 valence electrons. Is there a possibility for resonance or anything like that? No, there isn't. So let's go ahead and figure out our steric number. Here's one area of electron density, here's another, and here's a third. So go to 3 on your table, and you can see that we have no lone pair. So how would we refer to the overall geometry of this molecule? And it would be a trigonal planar molecule where the bond angles are 120 degrees, right? Now, as far as being polar versus nonpolar molecule, fluorine is extremely electronegative, right? Well, the question is, because of this particular geometry, how can one fluorine outcompete the other? If you think about it, the pool of this fluorine is canceled out by the contribution, or the component pools, if you will, of both of these fluorines. And that's just the same way, all the way around the molecule. So we would say that this boron trifluoride is a non-polar molecule. Our next molecule is xenon difluoride. Now xenon, it's a noble gas, right? It's in group 8, so it has 8 valence electrons. And we're going to add it to our 7 valence electrons on each fluorine, so 2 times 7. So we got 14 plus 8, that's 22. 22 total electrons. Alright, let's set it up. So xenon would be in the middle, and on each side of it would be a fluorine. Let's go ahead and complete the octets on the fluorines, and then we'll do our accounting for the electrons and see how many more we actually need. So here we go. 2, 4, 6, 8, 10, 12, 14, 16. So now we're going to put the rest on xenon. How about 18, 20, and 22? Ah, look at this. Remember, because of where xenon is positioned on the periodic table, since it's so low, it can have more than an octet. It's fine with more than an octet in its valence shell. So, okay, is there any possibility for resonance here? No, the answer is no. So yeah, this molecule is pretty good for us to start. We need to determine the steric number though on the xenon. So here's an area of electron density, here's another area, and then each of these lone pairs. So we're looking at a total of 5, a steric number of 5. Go to your table, go down to 5, okay? Now, we had 3 lone pair this time, go all the way across. What type of molecule is this? And if you're looking, you can see that it is indeed a linear molecule that has bond angles of 180 degrees. So basically, this is the shape of our molecule. Now, when it comes to electronegativity, the fluorines definitely are more electronegative than the xenon. So there's an overall pull in that direction. And then there's no difference in the electronegativity strength, if you will, this fluorine versus that one. So this one's able to pull just as much. So they cancel one another, right? So because neither one of the fluorines is out competing the other, we would just say that this molecule is nonpolar. Bromine pentafluoride. So bromine pentafluoride, okay? Well, what group is bromine in? And you can see that bromine is a halogen, so it's got 7 valence electrons, but notice Fluorine is a halogen as well. So we have 6 times 7 for a total of 42 valence electrons that we're going to account for. Great. Now, let's put our bromine in the middle. And I'm going to just kind of branch it off here and start adding fluorines. So, do this type of structure here. Oops, so I'll try to be consistent on both sides. Just to start with, that doesn't necessarily mean it's the shape, right? Let's make sure we have 42 electrons. So let's complete the octets on all of the fluorines. Okay, let's do our accounting. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. So we're missing 2 electrons. Well, we can put them on the bromine. Don't get freaked out by all these bonds, guys. Remember, bromine is well below the second period. If an element is below the second period, basically that means what that basically means is that they can accommodate more than an octet in their outermost shell. And such is the case. So now we have 42 electrons, and guys, this is it. Let's calculate our steric number here. So here's an area of electron density. Here's another one, and a few more. So we have 1, 2, 3, 4, 5, 6. Go down to 6 on your table. Once you're there, how many lone pairs did we end up having on the bromine? We had 1 lone pair. What is the shape of this molecule? It's called a square pyramid, or square pyramidal would be the molecular geometry. So now I'm going to redraw our molecule, and I'll make it look like the geometry that you see there on your table. So we have a fluorine here, we have a fluorine there, we have a fluorine here, and a fluorine there. And then one more. Right? Or is it inverted? Yeah, it's inverted. I'll draw it like that. I'll say fluorine, and then I'll put our lone pair down here on the bottom of the molecule. Okay, now let's determine if this is a polar molecule or not. So, fluorine is more electronegative than bromine. So what that means is there's going to be a pull in this direction. However, that pull is going to be canceled out by the pull on this fluorine. Okay, yeah, thank you. I'll go ahead and put my lone pairs. Let's be thorough. But do you see what I mean? As far as canceling out? And it just makes sense if they're the same element. Okay? Good. Now, the pull by this fluorine would be canceled by the pull on this one. So, we have one more fluorine though that has really no competition. So this whole region of the molecule would have more electron density. So we would say that this area of the molecule is overall more electronegative, while these other regions, especially this side, is more electropositive. So the answer is, or the answer to our question is yes, this bromine pentafluoride is definitely a polar molecule because these fluorines cancel one another out. However, we have one that has no competition. Now what about chlorine trifluoride? Chlorine trifluoride, okay? They're all group 7 elements, so we got 4 times 7 valence electrons gives us a total of 28 electrons that we'll account for. Chlorine is going to be in the middle, and it's going to be bonded to the 3 fluorines. So I'll just set it up like this. And I'm going to go ahead and start filling in the octet on the fluorines. And then we'll go through our process and make sure we'll do our total electron count. like we always do. All right, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We have a few more electrons to account for. Let's put them on the chlorine as lone pairs. I'll do it like here. So that'd be 26 and 28. Okay, interesting, right? Let's figure out our steric number on the chlorine. So here's an area of electron density. Here's another one. Here's another one. And then don't forget your lone pairs. Now, one thing I do want to do before we move further and actually look at our table is I want to make sure that this molecule makes sense, like this formation. Could there be double bonds? That's not typical that you'd have a double bond between halogens. But you never know. I mean, there's a lot of interesting molecular shapes out there. Let's go ahead and figure out our formal charge on the chlorine. And we know it's a group 7. Right now it has a total of 4 unbonded electrons, and then as far as bonds, 2, 4, 6 divided by 2 is 3. So its charge would be 0. What about for the each of the fluorines? Well, it's group 7 minus 6 unbonded electrons minus 2 divided by 2 is 1, and yeah, each of their formal charges is 0, so we can feel confident that this is a good structure to start working with. All right, now go to your table and look for the right number of, or the right steric number, and we're looking for the number 5. Okay, you're there. How many lone pairs did we end up having here? We had 2 lone pairs, so go to the right, and you can see that this is going to be a T-shaped molecule where the bond angles are less than 90 degrees. So it would really be, if I draw it correctly, it'd be this type of structure. T-shaped. And then we'll have here, and then of course we'll have the 2 lone pair. And then I'll fill in all the octets. Now let's start thinking about the molecule as a whole. Is it polar or not? Well, fluorine is more electronegative than the chlorine, so there would be a pull in this direction. And then that pull would get canceled out by the pull by this fluorine. And then we have a pull downward. Now there's no real direct competition for this particular fluorine, so yeah, that would create a region, an overall electronegative region, and then somewhat of a more electron positive region. So the answer is yes, this is indeed a polar molecule.